Hello and welcome to my next online tutorial where we're going to be talking about the second type of statistical test that you're going to be using, and that's going to be a t-test. You'll use a t-test when you're looking at two different samples or two different data sets and you want to see if they're statistically different. So for example, we're not looking for a relationship anymore like we were in correlation. We're looking to see if there's a difference. So for example, a difference between performance before and after training, something like that. First, though, we need to talk about hypothesis, because that's going to affect exactly what t-test we do. And a hypothesis is a theory that predicts a specific outcome. So let's say, for example, we have a predicted hypothesis. We call that our experimental or our alternate hypothesis. So that hypothesis might be that a drug improves a patient's condition, or advertising increases sales, or diet influences intelligence. Now, in addition to this alternative hypothesis, we need to set up a null hypothesis, which is the opposite. And it's basically that it's always that there's going to be no difference between the two separate sets of results. So your alternative hypothesis is always that there is going to be a difference, and your null hypothesis is always that there's not going to be a difference. So, let's say, for example, your null hypothesis is going to be there's no difference in a patient's condition before or after treatment with a drug. So your alternative hypothesis will be that there will be an improvement in the patient's condition after treatment. Notice we've started talking about a direction of change. So we're predicting an improvement in the patient's condition. So this means we're talking about a one-tailed test rather than a two-tailed test. So a two-tailed test, my hypothesis, would be that there'll be a change in the patient's condition after treatment. So I'm not predicting a direction in which it's going to move, I'm just saying there's going to be a change. Here, though, it's a one-tailed test, so I'm making it more specific because I'm predicting the direction, i.e. an improvement in the patient's condition. So let's talk a little bit more about what we mean by pairs and tails. So the prediction that there'll be an improvement in the patient's condition is also paired, as the patient used for comparison will be the same before and after treatment. So patient 1's results before treatment will be compared to patient 1's results after treatment, and they're the same group. So when do we use an unpaired test? Well, that'll be used at all other times. So for example, when the participants in each group are deliberately different. For example, if we were looking at the effect of training on experienced athletes versus novice athletes, and obviously those two athletes can't be in the same group. We can't compare directly one person to the other. So let's have a quick look at what that looks like on our distribution curve. So a two-tailed test, that's going to be looking for any results that lie in the blue outlying areas, both at the top end and at the bottom end of probability. If we have a one-tailed test, this is going to be purely looking at the probability of a result coming at one end of the scale. So in this example, in the upper end of the scale, as you can see below. So these hypotheses and the type of test, one or two-tailed, must always be stated. We also have to state how confident we want to be that results aren't by chance. So we generally use 99 and 95% certainty. So if we want to be 95% certain, we're testing to a 5% significance. And if we want to be 99% certain that a result isn't by fluke, then we're testing to a 1% significance. The easiest way to use to calculate t-test is either on Excel or to use an online function. So for example, this GraphPad calculator is pretty useful. Now what they spit out will vary depending on the product that you're using. And sometimes it'll spit out a t-value and sometimes it'll produce a p-value. Essentially, they're two ways of saying the same thing. But let's look at what they mean. So as I say, there's two results we can get, a p-value or a t-value, and don't get them confused. So the p-value gives you the probability, and the t-value, you need to compare that to a table to work out whether it's significant or not. And hopefully that'll become a bit more obvious when we go through some examples. So in order to interpret the results, you must know which is which. You must know which value your software is spitting out, is giving you, in order to look at it and see whether it's significant or not. So the p-value, let's think about this in terms of decimals. So 1.0 is 100% probability. So it's definitely going to happen. It's a certainty. So 0.5 is a 50% probability. And if we think of 0.05, that's a 5% probability. Okay, so a 5% probability that something's going to happen. Or a 95% certainty in our case, because remember, we're looking for an outlying figure. So we're looking for the chance that figure is lying outside of the 95% normal range. So if p is less than 0.05, there's a greater than 95% certainty that the two data sets are different. If the statistics is significant, we can reject the null hypothesis and accept the alternate hypothesis. If it's not significant, then we cannot reject the null hypothesis. So it has to work this way round. We always assume the null hypothesis is true until it's proved otherwise. So let's go through an example. Example 1. So we have 8 students and they time themselves on a cross-country run before and after training. So our null hypothesis is that there's no difference before and after training, and our alternate hypothesis is that there is a change in times. Now have a think. With that hypothesis, is that a one-tailed or a two-tailed test that I'm going to be doing? Hopefully you've decided that it's a two-tailed test because I haven't predicted a direction in which they're going to change. If I'd said that their times are going to improve or their performance will improve after training, that would be a one-tailed test, but I haven't, so I've just said there's going to be a change in the times. And we're going to look for a 95% confidence that these two data sets are separate. So here are my results. Now, which test are we going to use? This is paired data because there's 8 students or 8 participants, and we're going to compare student 1's time before training and student 1's time after training. So in effect, any differences between the group before training are going to be cancelled out because we're only comparing person 1 before training and person 1 after training, and person 2 before training, person 2 after training. So because there's 8 pairs, the degrees of freedom is n minus 1. So the degrees of freedom will be 7. And we've calculated that the t-value is 2.049, and I'm going to show you how to do that. So I'm going to use GraphPad to make this calculation. And I'm going to use this one here. So I've put my data in here, and I can choose to either paste or enter them in different rows, but I've cut and pasted them from my spreadsheet. And I've chosen here, where it says choose a test, I've chosen a paired t-test. Okay, so person 1 relates to person 1 afterwards here. Okay, I can't change the order this second group is in because one person here relates to their score here. So person 4 here, who's got 9 minutes, relates to person 4 here, who's got 8 minutes. So I can't change the order. I'm going to click calculate now, and that'll give me a load of information. So here is the important t-value. So t equals 2.049. And I can see there the degrees of freedom underneath are 7. So that's my t-value. T equals 2.049. Let's go back to the results. So that's my t-value. So what do I do with the t-value? With the t-value, I have to look at a table and decide whether the result is significant or not. So here's my table, and you can download this off Google, off the internet. They exist. They're standard tables. They're the same for all of your t-test calculations. So let's work out, is it significant? So we're going to look for the 95% confidence because that's what we're interested in. So we're looking for 0.05. We're looking for it to be, actually it's going to be two-tailed, not one-tailed. That's wrong, but it'll be two-tailed. So I'm looking in this column here. Okay, so level of significance for a two-tailed test, 0.05. All right, so I'm looking down this column, and I'm going to compare across. This is degrees of freedom here, so we said it was 7, didn't we? So our result is going to be 2.365. Now, the answer then, therefore, is that our t-statistic, 2.049 is not greater than 2.365. So if you read at the top here, it says critical values for t must be equal or more than the stated value to be significant. So our t statistic, 2.049, is not greater than the value that we get in the table of 2.365. Therefore, there is not a significant difference before and after training. Let's have a look at what the p-value gives us. So we can see the same thing looking at the p-value, but we just need to interpret the result differently. Our p-value is 0.079, and let me show you how to calculate this. So we can either get, if we go back to GraphPad, we can see that in GraphPad, and it spits it out up here. So 0.079, just here. That's our p-value. All right. We can also calculate it in Excel. So if this is our data for Excel, I can click on the cell, enter equals, and I'm going to enter, double click on t-test. Now it's a little bit complicated here. You just need to stay with me a bit. So for array 1, see where all this box underneath has opened up? For array 1, I'm just going to put my first set of statistics. I'm then going to click down here on array 2 and enter, drag and drop my second load of statistics. Now there's two other boxes underneath. So tails, if I click 1, that means it's a one-tailed test. If I click 2, it's going to be a two-tailed test. So mine was a two-tailed test because I didn't predict the direction of the movement. And then type, so 1 means that it's paired, 2 or 3 means that it's unpaired. So I'm going to click 1 because it was a paired test. And that will give me exactly the same p-value. So Excel gives you a p-value. The advantage of using GraphPad, it gives you a t-value and a p-value. So that's how we've worked that out. Let's get back to the presentation. So our p-value, as we've just seen, is 0.0796. And we can work that out from Excel or from GraphPad. So p is not less than 0.05. So the probability that the two data sets are separate is not greater than 95%. So therefore we must accept the null hypothesis that there is no difference before and after training. Let's look at another example now. So times are recorded for a person to travel 2 routes to work. And we want to find out which one is the quickest and see if there is a significant difference between the 2 routes. So this person travels route A or route B. Now, this is going to be unpaired data because the same person is traveling route A as traveling route B. So we can rearrange this order of route B, and it doesn't have any impact on our results. In fact, if you look at it, we've actually got 1 fewer measurement for route B than we have route A. Now that's perfectly okay, we can do that. So our null hypothesis is there's no difference between the times of route A and route B. The alternative hypothesis is of course that there is a difference between the times taken to travel route A and route B. And again, we're looking for a 95% confidence. So the data isn't paired, i.e. the numbers in the 2 lists are in no particular order and could be rearranged. So here the degrees of freedom can be calculated by n minus 2, where n is the number of pieces of data. So the degrees of freedom is 11 minus 2, so it's 9. And we can calculate our t-value, which is 2.928, and we've done that using GraphPad. So let me show you how we've done that. So these are my 2 sets of data. You can see I've just cut and paste them. This time I'm going to select an unpaired t-test, and I'm going to calculate now. There we go, and we can see the t-value, 2.928. That's what we've come out with. You'll also notice as well, GraphPad has given us the p-value as well up here. So the t-value, and it's got the degrees of freedom at the bottom. So the t-value is 2.928. That's what we're interested in at the moment. Let's look. So let's look on our table again and see if that's significant. Again, we're looking for 95% significance, or 0.05. It's a 2-tailed test. So 0.05 for a 2-tailed test. This is the column we're using. Degrees of freedom is going to be 9. So that's the value we're looking for. So the answer is yes. Our statistic our t-value 2.928 is greater than the value given in the table, 2.262. So there is a significant difference in routes A or routes B. So would it be significant at the 99% confidence interval? Well, let's have a look. So this is the column. So 99% interval would be 0.01. So this is the 0.01 or the 99% confidence interval. Again, we can look down our table and find degrees of freedom 9, and it's 3.250. So is it greater than 3.250? No, it's not. So 2.928, our t-value, is not greater than 3.250 here on the table. So it's not significant at the 99% interval. Again, we can see the same thing looking at the p-value. So we've calculated the p-value. That was on GraphPad, if you remember. Just up here. 0.0168. So our p-value is 0.0168. And p is less than 0.05, so the probability is greater than 95%. But it's not less than 0.01. So our probability is not greater than 99%. So we can say that the null hypothesis must be rejected, and we must accept our alternative hypothesis that there is a difference, there's a statistically significant difference between the times taken for route A and for route B. So I'm just going to show you very quickly how you can do that on Excel. So this is our data again. Very, very similar to what we did before. So equals, double click over here on t-test, and I'm going to go for array 1, array 2, but this time, so we're going two-tailed again, but this time we're having a paired, so two sample equal variance. Just use this. This is the easiest way to think of this. Don't worry about the differences in assumed variance. So the type is 2, and that should give us our p-value, here we are, of 0.016, and that's exactly what we came out with at GraphPad. So hopefully that's given you a bit more of an insight about hypotheses, about t-testing, and about how we can use it to find the statistical difference between two sets of data. Remember, that's what we're looking for. So correlation is looking for a pattern between two sets of data, whereas a t-test is looking for a difference between two sets of data. Any questions, send me an email. Thanks very much.